Okay, let's continue with the chapter about silicates. In the last class, we discussed two-dimensional silicates, also called phyllosilicates, and we have learned that they are so-called one-to-one phyllosilicates, where one tetrahedral layer is fused with one octahedral layer, and they are so-called two-to-one phyllosilicates, in which a tetrahedral layer is being while two tetrahedral layers are sandwiching one octahedral layer. So one of the one-to-one phyllosilicates that we encountered was the serpentine, and in serpentine we have a so-called trioctahedral layer. So that means that all octahedral holes within that layer is being filled. Now, this structure has the property that the octahedral layer consumes slightly more space than the tetrahedral layer. And that is now giving potential for the bending of that layer, okay? And the layer would bend so that the more space-consuming octahedral layer would point to the outside, and the less space-consuming tetrahedral layer would point to the inside. And what can then happen is that these bent layers close to form actually tubes. Okay, so this is then known under the name fibrous serpentine or chrysotile. So now this results in the closing of the layers to form tubes results in a fiber structure, and you see here electron microscopy images of these fibers. Okay, and you see that these fibers are made of multiple sheets that are folded to form tubes, whereby these tubes have a diameter of approximately, as you can see here, 20 nanometers. And inside, there are hollow channels that have diameters of approximately 5 nanometers. So these fibers can have a length of up to 4 centimeters. So this chrysotile is one form of asbestos because its fibrous structures have fibrous structure. It can be used in order to reinforce other materials. So this form of asbestos is the least toxic form of asbestos and is still used in some applications up to date. So it does not suspend in air, and it's still biodegradable. So today, 99% of asbestos is actually chrysotile type asbestos. So these fibers are extremely flexible, they are extremely heat resistant, they are non-flammable, they are excellent thermal insulators, and they are also very cheap. You find them even as minerals in nature. You can just mine them in certain locations. So when you add the chrysotile to cement, you get so-called asbestos cement, which gives the which increases the mechanical properties. So get increased tensile strength, compression resistance, and durability, so that you can produce thinner and lighter products. You can also add these fibers to other products in order to mechanically reinforce them. Okay, so this is the last part about the two-dimensional silicates. We can now move over to the three-dimensional silicates. which are also known as tectosilicates. Now, the most simple tectosilicate is the silicon dioxide itself. So it's the parent compound of all silicates. And we have already encountered hypothetical forms of SiO2 previously, in particular layered structures of SiO2. But we have learned that these layered structures are not being realized because the three-dimensional structures are thermodynamically more stable. Okay, so let us look at these structures in more detail. So you see here the phase diagram of SiO2. So in this phase diagram, you have here the temperature to the right side and the pressure as the y coordinate. And you see that SiO2 has fairly many phases. So what is the phase that we find at ambient pressure and ambient temperature? This phase is the so-called low quartz, as you see here. It's called low quartz because it's the low temperature form of quartz. So that means there's also a high temperature form of quartz, which is called high quartz accordingly, which is shown here in green. So you see that this form of quartz is stable at higher temperature and also in this region here at higher pressure. So there are two other high temperature polymorphs of SiO2. That's the tridamide. Okay, so if you stay at relatively low pressure and go higher with the temperature, then your high quartz will convert into tridamide, and at even higher temperatures, at approximately 1500 degrees Celsius, you will have Chrysotile as a thermodynamically stable form, and above 1600 degrees Celsius, then SiO2 will be thermodynamically stable as a liquid. Okay. So these are the four, low pressure forms of silicon dioxide. In addition to that, you also have high pressure polymorphs. So if you go above about 20,000 times the atmospheric pressure, or 20 kilobars, then, or 2 gigapascals, then you enter the stability field of the coesite, and you see that the coesite is a very wide stability field here in yellow. If you go to even higher pressures, then above approximately 7.5 gigapascals or 75 kilobars, you enter the stability of the stisovite, and at extremely high pressures, there are even other high pressure polymorphs of SiO2 possible that we are not going to discuss in more detail. We have actually encountered the stisovite already when we discussed silicate phases in which we have the coordination number higher than 4. So remember, in stisovite, we have the rutile structure in which silicon has the coordination number of 6, and oxygen has the coordination number of 3. So all the other phases here, they have all silicons with the coordination number of 4 and oxygen with the coordination number of 2. So let us look at these structures in more detail. So let us look at the quartz structure in particular, the low quartz structure. Remember, we actually discussed that structure to some extent already when we discussed screw axes. So the quartz structure contains both 3-fold screw axes as well as 6-fold screw axes. Okay, you see here 3-fold, one 3-fold screw axis. And over here, you see that these individual chains are interconnected with each other, okay, to form overall a three-dimensional structure. Okay. So now, in addition to that, you also have 6-1 and or 6-5 screw axes, depending on which enantiomorphic form of silicon dioxide you are looking at. We have also discussed this previously in the class. So you see here the tetrahedra that belong to such a 6-fold screw axis, okay? And you see that you have to go 6 tetrahedra until you reach a tetrahedron which is, well, identical to a previous one. So for instance, if we start with this one and we say this is the first one, and this is the second one, this is the third one, this is the fourth one, that's the fifth one, and that's the sixth one, and the seventh one, here, this one, will be identical to the first one. You can see that you can translate the first one here along the C direction in the crystal so that it starts overlapping with this tetrahedron here. And that translation holds for all the tetrahedra. So for instance, if you put yourself on this one, then this one would be the one which is analogous in the next repeating unit. Okay, so here in this picture, you see again that every tetrahedron that belongs to a 3-fold screw axis also belongs to a 6-fold screw axis. So here's, you see here in different colors, again, the 3-fold screw axes. Okay, so for instance, this one here are tetrahedra that belong to a particular 3-fold screw axis. So these blue ones here belong to a particular 3-fold screw axis. So these purple ones belong to a particular screw axis. And these green ones also belong to a particular screw axis. Okay? But each tetrahedron also belongs to a 6-fold screw axis, and that's indicated here by light and bold colors respectively. So all tetrahedra that are in bold belong to the same 6-fold screw axis, okay? So we can, for instance, start with this tetrahedron here, and then you see that the next tetrahedron is this purple one, which is in bold. The next one would be that one, also purple and bold. This one here would be blue and bold. This one would be blue and bold. Then we have these two green ones in bold. Okay. And then we would have another another 2 purple ones, another 2 blue ones, and then another 2 green ones. Okay. So overall, we would have to go 6 tetrahedra until we meet tetrahedron, which is identical to the previous one. So if this is the first one, this is the second one, the third one, the fourth one, to the fifth one, and that's the sixth one. So this one here would be identical to that one here. It would just be in the next repeating unit. All right. So in this view, we are looking perpendicular to the C-axis. Now let us look along the C-axis, where you can see these screw axes in a different way. So the crystal structure of quartz along the C-axis looks like this. And you see here the 6-fold screw axis and the 3-fold screw axis as part of the structures. Okay. So the colors yellow, green, and blue indicate increasing distance from the plane of the diagram. Okay. So if we say yellow is the closest to us, then this one would be further away from us, and this one would be either further away from us. Okay. So in this case, we would actually rotate counterclockwise. along the screw axis. Okay, so these three tetrahedra would belong to the same threefold screw axis, which would turn counterclockwise. Okay, then there are again six tetrahedra that belong to a six-fold screw axis, which would run here. So in this case, we would have six tetrahedra that would belong to a particular screw axis. So 1, 2, 3, 4, 5, 6 tetrahedra overall. In addition to that, we also have a twofold axis in the crystal structure. The twofold axis actually sits here. It goes through the edges of the tetrahedra. That axis would be a fourfold axis if there were not the additional 3- and 6-fold screw axes. All right, so these considerations should allow you to understand the overall crystal structure of quartz. So now, in addition to this low quartz, it's also sometimes called the alpha form of quartz. There is also a high temperature form of quartz, the high quartz, also sometimes called the beta form of quartz. And the alpha form can convert into the beta form via a so-called displacive phase transition. Okay, and you see this displacive phase transition happening here. So what do we mean by displacive phase transition? In this case, we're talking about a phase transition that can occur without any chemical bonds being cleaved. Rather than that, the polyhedra within the crystal structure just rotate so that a new crystal structure is being adopted. And you see that actually here. So you see here the alpha form of the beta quartz converting into the beta form. You see that the beta form has now only these triangular channels that form at the expense of this hexagonal channel. So that's the alpha form. Now we have the beta form. Okay. So of course that process is reversible. As you actually cool beta quartz, the beta quartz can convert back into the alpha form. So this is called a displacive phase transition. This is opposite to a phase transition, which is called a reconstructive phase transition. When we have reconstructive phase transitions, then that means that we actually have to cleave and reconstruct bonds in order to make such a phase transition happen. For that reason, these reconstructive phase transitions are typically associated with significantly higher activation energies in comparison to the displacive phase transitions. So now, with the exception of the alpha to beta phase transition, all other phase transitions between the silicon dioxide polymorphs are reconstructive phase transitions. Before we go to the other phases, let us briefly discuss one very interesting property of quartz. So quartz is known to be a piezoelectric material, and it finds applications as such in, for example, sound detection, as pressure sensors, or in micro balances. So what is the piezoelectric effect? the piezoelectric effect occurs when you have a non-centrosymmetric crystal structure, and the quartz structure is a non-centrosymmetric crystal structure. That means that we do not have an inversion symmetry within the crystal. That means we have no inversion center within the crystal. And for that reason, when we apply a mechanical force to the crystal, the tetrahedra can actually slightly rotate, okay? And this rotation induces a dipole moment in the crystal, okay? So you have actually a dipole moment across a macroscopic crystal, and that means that opposite crystal, that there's a potential building up along opposite crystal faces, and that potential can simply be measured with a voltmeter, right? So as you actually press on your crystal, two opposite faces of the crystal will show a different potential that you can measure. Okay, so in the case of quartz, the crystal does not overall have a dipole moment, no permanent dipole moment, even though there is no inversion symmetry. Actually, each tetrahedron does have a dipole moment, but the tetrahedra are arranged in the crystal structure so the dipole moments cancel out. Okay, so there was no overall dipole moment in the crystal, but as soon as you actually apply a pressure to two opposite crystal faces, these two dipole moments, they don't cancel out exactly anymore, resulting in an overall dipole moment within the crystal. So if you have there are also crystals that have a permanent dipole moment in the crystal structure. In this case, we call this crystal pyroelectric. Okay, so in this case, we actually produce a voltage along two crystal faces upon temperature changes, or at least it would be more precise to say the voltage changes upon temperature change. Okay, so that is simply because of thermal expansion. Okay, as I increase my temperature, my crystal expands to some extent. Okay, and of course that influences the overall dipole that I have across the two crystal surfaces. So in a way, I can therefore use such a pyroelectric crystal in order to measure temperature via voltage. So an example for that is tourmaline, which is a boron containing ring silicate. So tourmaline is an example of a material which shows pyroelectricity. Okay, so now because of the piezoelectric properties of quartz, quartz is produced industrially. So quartz is a very common mineral, but rarely you find quartz crystals that have the crystal quality so that you can use them for piezoelectric applications. Okay, therefore, quartz is grown, quartz crystals are grown industrially at a very large scale, and I would like to briefly talk about how this is being done. So you grow a quartz crystal in a process which is called a hydrothermal growth. And in this hydrothermal growth, you apply a temperature gradient in order to make the crystals grow. So you see here schematically the experimental setup. So you have here a high pressure autoclave with a high aspect ratio that allows you to produce a large temperature gradient, and you have two zones. Okay, so this is the dissolution zone here, the lower one, and this is the growth zone, which is the upper one. And these two zones are separated by a so-called baffle, and that baffle is nothing else but a disk that has holes. So the baffle allows you to increase the temperature gradient, but it also allows you the mass transport from the growth, from the dissolution zone into the growth zone. Okay, so in the dissolution zone, you have your so-called nutrient, and your nutrient is a form of silicon dioxide. Okay, it can be, for instance, natural forms of quartz, such as lasca. It can be xerogels and other silica sources. Okay, and then in the growth zone, you place silicon dioxide seed crystals. Okay, particular seed crystal plates. Okay, in which basically the C direction of the crystal stands perpendicular to the plate. And the plates have this orientation because the crystal grows the fastest in Z direction. Therefore, you want to maximize the surface of the crystal perpendicular to the Z direction. Okay. So now you can apply a temperature gradient within the autoclave. So typically the temperature gradient is between 5 and 50 degrees Celsius at a temperature range between 350 and 400 degrees Celsius. So the bottom zone is always somewhat hotter than the growth zone. So the nutrient dissolves in the dissolution zone and then is transported through the baffle into the top zone, which is somewhat cooler, and therefore the solution becomes oversaturated. Okay, because of the oversaturation of the solution, your seed crystals that you actually place into your top zone start to grow. Okay, so you perform this crystal growth at a pressure of approximately 0.15 gigapascals or 1,500 atmospheres. So this hydrothermal crystal growth is scalable to the industrial scale. You see here a picture, okay, in which you have your grown seed crystals, okay, many of them inside of the autoclave, which actually mounted in the ground. So typically you mount these huge autoclaves in the ground because it's the safest way to mount them. As you can easily imagine, such a very large autoclave system represents some kind of a bomb. So if your autoclave fails, the smallest damage is done when these autoclaves are actually inserted into the ground. All right. So let's look at the hydrothermal crystal growth in a little bit in more depth. What I have forgotten to say is, of course, that in the autoclave you also have a mineralizer. Okay, and that mineralizer is typically either a sodium carbonate solution or a sodium hydroxide solution. Okay, so these basic solutions, they help dissolving the nutrient and increase the solubility of the nutrient in the aqueous solution. Okay, so generally, the higher the concentration of the silicon dioxide in the mineralizer, the faster the crystal grows. Okay, so you see here the pressure that is in the autoclave as a function of the temperature and as a function of the so-called fill rate. Okay, so the fill rate is the percentage by which the autoclave is being filled at room temperature. Okay, so for instance, a 65% fill rate means that at room temperature, 65% of the internal volume of the autoclave is filled with the mineralizer, okay, mineralizing liquid. 75% means that the 3/4 of the autoclave is being filled with a mineralizer and so forth. So we see here how the pressure increases as a function of the temperature for these different fill rates. Okay, so initially for all the fill rates, the pressure only increases very slowly. That is because the pressure in the autoclave is basically only a function of the vapor pressure of the water. Okay, however, due to thermal expansion, the autoclave gets fuller and fuller with liquid water as you increase the temperature. And at one point, your autoclave is completely full with liquid water. Okay, and at this point, your pressure increases linearly. Okay, and it increases very steeply because the pressure is now no longer determined by the vapor pressure of the water inside of the autoclave. Now you see the temperature at which that steep increase happens depends on the fill rate. Okay, so at very high fill rates like 89%, this steep increase happens already at temperature close to 200 degrees Celsius. At 65% fill rate, for instance, that steep increase only happens above 300 degrees Celsius. Okay, so you can understand this even better when you look actually at this diagram here. So here we have liquid fill levels and how well the percentage of liquid filling the autoclave changes as we increase the temperature. So here we have, for instance, 80% fill at 25 degrees Celsius. And you can see that the autoclave fills more with the liquid due to thermal expansion, okay, as we go up the temperature. And at about 250 degrees Celsius, the autoclave is completely filled, okay? So above the supercritical temperature of the water, which is 374 degrees Celsius, then our liquid water transforms into supercritical state. So if we start at 50% fill, we have also thermal expansion of the water, okay? But we have, well, more gas phase to fill with the liquid. Therefore, the autoclave is full only at a significantly higher temperature, in this case at about 360 degrees Celsius. Again, above 374 degrees Celsius, we have water then in the supercritical state. So now there is, however, a so-called critical fill rate, and this is the fill rate at which the fraction of the liquid component and the fraction of the gaseous component within the autoclave do not change anymore with the temperature. Okay, and that is because there are actually two opposite effects. So I have mentioned thus far actually only one. So as you increase the temperature, there is thermal expansion of the liquid, and that tends to increase the volume of the liquid. However, there's also another effect, which is that there's more vapor pressure at higher temperature, and for that reason, more water molecules tend to go into the gas phase when you increase the temperature. And these two effects actually oppose each other. So now, above the critical fill rate, the thermal expansion of the liquid dominates the overall behavior, while below the critical fill rate, the vapor pressure effect is dominant. And at the critical fill rate, which is exactly 32%, these effects are exactly equal. So the ratio between the volume of the gas phase and the liquid phase is exactly constant until, of course, the critical temperature, where both the liquid and the gaseous phase convert into the supercritical phase. All right. So below the critical fill rate, let's say a 10% fill, the opposite would happen. Okay, we'd still have thermal expansion of the liquid, but we have so much more volume available that can take up liquid water evaporating due to increased vapor pressure, so that overall the volume of the gas phase increases at the expense of the volume of the liquid phase until at a particular temperature we have only the gas phase present. All right. So now in practice, the autoclaves are operated at fairly high fill rates of 80 to 85%. So why is that done so? One would think, well, I can't fill my autoclave already at significantly lower fill rates with liquid water completely and make my crystals grow. And I can do my crystal growth at significantly lower pressures, which is experimentally significantly easier to perform. So why would I want to go to these high fill rates that increase my pressure so much? The reason for that is that the solubility of the silicon dioxide in the mineralizer is strongly dependent on the pressure, which is directly linked to the density in the respective phase. So you see here that at 1,000 atmospheres of pressure, you see that the solubility of my silicon dioxide increases the further I increase the temperature. So even if I am in the supercritical region, my solubility further increases. Okay, and because my solubility is the highest, my quartz growth rate is the highest. Okay, so now you see here at 750 atmospheres, we also first have an increase of solubility, but above the supercritical temperature, the curve becomes very flat. I cannot much further increase the solubility of the silicon dioxide. You see, if I go to even lower pressures associated with even smaller fill rates, my solubility even becomes reversed in the supercritical phase. Okay, that's of course something which is unwanted because crystal growth rates increase with increasing temperature. So you see here that if I go to even lower fill rates and even lower pressures, the solubility even starts to decrease already somewhat before the supercritical temperature is being reached. Okay, so this is the reason why we choose high fill rates for the hydrothermal growth of quartz, even though this comes at the convenience of working with significantly higher pressures. All right, so this was a brief excursion into the field of hydrothermal quartz crystal growth. So now let us consider the other phases of silicon dioxide, which we haven't discussed yet. So tridamide is another phase. It's actually the high temperature phase above the high quartz. And in tridamide, we have a so-called hexagonal version of cristobalite. So actually we have a wurtzite derived structure. Actually, we have a wurtzite derived structure. So remember, in wurtzite was a polymorph of zinc sulfide, whereby we had a hexagonal close-packed structure of sulfur with 50% of the tetrahedral holes filled with zinc. So now on the tridamide, we have silicon making a hexagonally close-packed structure of spheres, whereby 50% of the tetrahedral holes are filled with additional silicon atoms, and then the oxygen atoms sit in between the silicon atoms. So this is a little hard to comprehend, therefore we better actually focus on another view, how to understand the tridamide structure. One can understand it also the following way. You see here, you have here chains of pairs of tetrahedra in the structure. So those which are identical have the same color. You see there are two kinds, whereby the green ones here, they interconnect these yellow ones. Okay, so now in this view here, you have actually two chains of the yellow ones and two chains of the green ones. And you see that they're now interconnected with each other to form here these six-membered rings. So if you rotate this structure by 90 degrees so that these six-membered rings here point to the front, then you actually arrive at this structure here. Okay, so this is how you can understand the tridamide structure. So now, in addition to the tridamide, we have also the cristobalite as a high temperature form. That's the highest temperature form at ambient pressure. So this derives from the zinc blende structure in the following way. So we have the silicon atoms that make the cubic close packed structure. And we have additional silicon atoms that occupy 50% of the tetrahedral holes. Okay, you see that here. And now the oxygen atoms, they bridge the silicon atoms, which sit on the sphere sides and the tetrahedral holes respectively. Okay, so you see here an oxygen that bridges that silicon on a tetrahedral hole and that silicon here on the sphere side. So this oxygen here bridges, well, a silicon in the tetrahedral hole and a silicon on the sphere side, and so forth. Okay. So last but not least, we have the coesite. So the coesite is a high pressure polymorph of silicon dioxide. It can be understood the following way. You see here that there are 4-membered rings of tetrahedra, and these 4-membered rings of tetrahedra, they build chains. Okay, and these chains actually form layers. Okay, so here's the first chain, here's the second chain, here's the third chain, and here's the fourth chain, and they all lie within a plane. And then you have other chains of 4-membered rings, shown here in light blue, okay, which sit above that first layer and form additional layers. Okay, so here would be the second chain, and here is the third chain. Okay, and now these light blue chains, they share tetrahedra with the dark blue chains, so that overall a 3-dimensional structure is resulting. Okay. All right. Now, so far we have discussed only forms of silicon dioxide, but not actually silicates with actually anionic structures, anionic silicate structures. In order to realize that, we have to substitute some silicon atoms by other atoms in the framework, so that the formal negative charge is present in the anionic structure. So we can do this, for instance, by replacing silicon by aluminum, because tetraaluminum has 1- negative charge added. The same with gallium. When we have a divalent ion, then there are even 2 formal negative charges at the ion. Okay. So if we replace some of the silicons in quartz, cristobalite, or tridymite, then these structures become anionic and now need to be charge compensated by cations. And we call these structures then filled quartz, cristobalite, and trimonite structures, okay? Because the voids within these framework structures are filled with countercations. Okay. So examples for filled cristobalite structures are, for instance, this sodium zinc silicate, okay, or this sodium alumina silicate, okay. So in this example here, some 50% of the silicons are substituted by zinc, and here 50% of the silicons are substituted by aluminum, okay? Because zinc has formally 2 negative charges, we need more countercations, the sodium ions, in comparison to this alumosilicate here. So example for filled tridymite structures are, for instance, nepheline. It's a mineral, it's a potassium, sodium alumosilicate. It's also known as a barium zincate. So filled forms of quartz are also known. For example, the eucryptite. We have a quartz structure in which some of the silicons are substituted by aluminums, and then the anionic charge in the framework is charge compensated by a lithium. Okay, so filled versions of the coesite structure are not known. That is because the coesite structure is already too dense. Remember, the coesite structure, the high pressure polymorph of SiO2, it's too dense in order to accommodate smaller cations. All right, then let's stop at this point.